Glad you're here. Had a good week so far? Yep, so far so good for me. Oh, I'm sorry, that's no fun at all. Okay, yes, if you're not here, just make sure you watch the recording. So, for this week, we have two things that we're going to do related to our labs, and that's why you see the materials up here in the chat part that's up here. I'm going to actually get rid of this for a moment. You'll see it's broken into two parts. One is a lab that we're going to do together in class. One is an activity that you will do after class. You'll need materials for both, but I wanted to make it easier for you to be able to differentiate. The one that you need for after class, you don't have to have those materials with you now. No issues there at all. It's something you're going to do separately, so there's not really a concern about having that ready to go. Don't worry about that. Okay. So, some info to what we're going to do today, kind of some help with it. We're going to talk a little bit about Newton's laws. We're going to talk a little bit about some other physics related topics to help you get a bit more comfortable with our content. We will do our lab, and then we will get to have a conversation about what you need for your outside of class activity. For this, there should be four of these. Okay. All right. So let's go ahead and say our word of prayer and get started here. All right. So here we go. Dear Heavenly Father, I thank you for this day. I thank you for our time here together. Thank you for the many blessings that you have given us. And God, I just ask that you would be here with us, that you would lead us and guide us, God, and that you would use us to spread your word to others. You would use us to glorify you and to bring others to you. Use us to lift other people. God, we just love you and thank you for the many people that you have put in our lives. We pray blessings over them today. Pray your peace and strength and comfort over them and just health and wellness. God, we pray for those who are not feeling well. God, just touch them, give them strength and peace and completely healed. God, we love you and we thank you. We ask these things in your name. Amen. There it goes. So let's start with our fun here of our brain stretches. Remember, just like before, we'll get a chance for all of us to look at them and then we'll go through and give answers. So no giving away the fun here. Okay, so let everybody have a chance to look at these. Then we will put up our randomizer to let someone choose first. And then we'll go through and let everyone put in answers. Don't worry about what the randomizer said. Remember, it's basically just whatever we ended with the week before. Give it just a few minutes. Okay, wait, why are we giving answers? We specifically said do not give any answers until we have an opportunity for people to get that. Remember I said don't pay any attention to the name that's there. That's the name from who went last week. Yes, I said everybody needs a chance to do it. Yep. Remember, Zachary, you should have remembered you went first last time. Oh, yeah. All right. Feel free to give answers. That kind of got ruined. So go ahead and put everybody's answers in there now. It doesn't make any difference at this point. You can all just put them in. Good. Several of you still putting answers in. You only need to put an answer in one time. We want everybody to have an opportunity to make a guess. So one answer per person and let everybody get an answer in. Don't make me call out your name. That's no fun. Okay. So let's see who didn't get an answer in here so that everybody can have an opportunity. Good. Correct answer for this one is free for all. Free for all. There you go. Kind of fun. All right. Next. Try this one. No clues, no hints. No guessing till we say it's time. Oh, yes. Free because it's $0 and for alls. So free for all. Okay, here we go. Our person who will guess first on this is going to be Noah. All right, Noah. Okay, good. So everybody put in a guess. This is your time. Make a guess. Good. Several of you have put in answers. If you've already put one in, you shouldn't be typing. But if you haven't put one in, you should be typing. Everybody gets a chance. Good. Most of us have done this. So this is a no escape. So no escape. Yep. There you go. Still got some of us who aren't guessing like we're supposed to be, but it's okay if you're saying, hey, I don't know. That's perfectly fine. Definitely yes. All right. One more to try before we get off and running. Here's our last one. Take a peek at this. No, it's not. We haven't spun forever. Everybody needs a chance to actually think about it. You guys get so busy typing that I'm going to probably have to pause typing when we're during thinking time because you can't help yourself. No restraint on that. You just start typing, but everybody needs time to process first. It's only fair. So let's see. Our next person to go with this is going to be Colton. Colton, if you have a guess, you can put it in there first. Okay. Everybody put your guesses in if you have them. Good. Lots of people with answers in. So for this one, it is things are getting out of hand. Can you see it? Things are getting out of hand. Look at the picture. Hmm. All the fun. Good. So these are pictures that are helping you to figure out all the fun. I know, and to get your brain working a little bit. That's the whole point. All right, let's get into our content a little bit so we have time to get through our lab, and talk about the extra lab. How's that? So, our first conversation is about what motion really is. What does it mean? So, this is going to kind of sound like an odd question, but how do you know if an object is in motion? How do you know if an object is in motion? Okay, just reading all your comments here. How do you know if an object is in motion? Okay, good. Several of you are typing, so I'm trying to give you time to finish up. Good. So, if you're trying to a lot of you guys are answering questions, but they're not actually the question I'm asking. You're giving answers, but think about the question I'm asking. How do you know if an object is in motion? Because a lot of us are saying things like, well, if you see it, it's in motion. But think about it. It could be in motion and moving slowly so much so that your eyes can't detect it. And some of you are talking about if it's in motion, it's going to stay right. But what does that mean for it to be in motion? What does that mean? No, I'm asking you to think about something that seems a little small and easy, but it's actually harder to explain if you're not careful. Okay. Okay. So if I had to explain what I mean when I say an object is in motion, if I'm talking about it personally, I'm going to say something like an object is in motion when its position is changing. Because if I simply say it's in motion when it's moving, a lot of times we define that movement by our own observations. And that can be a little confusing if you define it with something like that. But if we say it is in motion when its position is changing, it goes back to the ideas that we were talking about for fundamental building blocks in our reading and in our examples here. So if you're looking at when the position of an object changes, you have to compare that position to what we call a reference point. That reference point could be your eye, it could be where you're standing, it could be somewhere else, it could be, you know, a stationary object compared to a moving car, things like that. But we compare that position change to some reference point. That's how we know that an object is moving. Its position is changing compared to a reference point. So here is one way we're going to do that. One way distance or position change, distance motion is going to be measured is by measuring its speed. So the speed of an object, and you're going to think it's funny that I'm explaining to you about speed, but you'll know more when we start talking about speed versus velocity, why it's important that definitions are super clear. Okay. So the speed of an object is comparing the distance, how far an object traveled, to the time, how long that an object traveled. Okay. So speed is going to compare the distance an object travels to the time that an object travels. So what would be some units that you could use for speed? Okay. So it has to compare distance and time. So kilometers, miles, meters, feet, those couldn't be used because they're not comparing a distance measurement to a time measurement. That's what I want to make sure we highlight in this conversation. Okay. If you talk about miles per hour, that's fine. You wouldn't want to talk about Kelvin per hour. Kelvin per hour is a temperature measure. Yep, miles per hour is fine, but meters per second, kilometers per hour, inches per minute, anything where you're measuring a distance unit and a time unit, you could use as a speed unit. You simply have to be comparing distance units and time units. Good. Okay, so now when we hear the term velocity, the it is often used interchangeably with the word speed, but those are not the same. Speed only tells us how quickly an object moves, how quickly it is able to travel a distance. Velocity tells us that plus one more thing. Velocity tells us how quickly an object can move and the direction it's moving. So velocity is actually more detailed, more specific than speed. Okay. So it includes both the how quickly it's moving and the direction that it's moving. Good. Okay. Comfortable with the difference between those two? Good. So when we're talking about direction, sometimes it's only positive versus negative. Sometimes it is, a directional word like north or to the right or something like that. Those are all examples. Good. All right. So when we talk about acceleration, you'll notice I'm giving you all of these definitions up front and talking through what they mean, not just saying, hey, I know you read about these last week. Let's keep going. I'm trying to slow down and go through what they actually mean so that when we start putting them in the context of all of these laws, calculations, all the things, we better understand what we're dealing with. So when we talk about acceleration, it is a measure of how fast the velocity is changing over time. Okay. So some ways that an object could be accelerating. If the object is speeding up, if an object is slowing down, or if an object is changing directions. All of those are example of accelerating. Those are all examples of acceleration. An object is speeding up, an object is slowing down, an object is changing directions. All of those count. All right, another new one. How about force? I know our weird little animation here, it doesn't like our guy, but one other idea that's going to come in for what we're looking at in our discussion of Newton's laws is going to be the idea of force. Okay. So, force is anything that causes an acceleration. All accelerations are caused by forces. Okay. So, an, a force could be a push, it could be a pull, but in some way it changes the acceleration. Meaning, if an object is not moving, it's not going to start moving unless you apply a force of some type. Okay. Like we said, it could be either a push or a pull. Okay. The other word that's kind of confusing for you, sometimes you guys use it interchangeably with the word weight, but the word that can sometimes be a little confusing for you as we get into Newton's laws, these are the things that you guys kind of mix up in your brain, is the idea of mass. So, mass is a measure of how much matter is in an object. Okay. So, it's a measure of how much stuff an object has, things like atoms or molecules that are in that particular thing, whatever the thing happens to be. Okay. So, if an object with mass is not moving, it's not just going to start moving on its own. And a lot of times you guys think, well, if I'm sitting here, even if I were sitting perfectly still, then I just move on my own. But your muscles are applying a force to your body to cause it to move, cause your eyes to open, to cause your muscles to move, um, and get up and walk, whatever it happens to be. That's still a force that's being applied to the mass of your body. It's going to take some sort of effort, whether that effort is pushing, that effort is pulling, that effort is um, both some sort of effort to put an object into motion. Okay. Also, the opposite is true. If it's already moving, it's going to take some effort to change that movement, whether that be speed it up, slow it down, stop it. It's going to take effort to do that as well. Okay. So, because there is an amount of effort that it requires to do this, it feels like the objects, and Aristotle kind of described it this way too, like an object is resisting being moved, like it doesn't want to move. I mean, the pencil doesn't really have emotion, so saying it doesn't want to move is kind of silly, but it's this natural resistance to change, but it's not resistance to movement, it's resistance to change at all. Whatever it's doing, it just wants to keep doing that, which I think you guys should be able to understand. Teens and tweens, that's like your calling card. Whatever I'm doing, I just want to keep doing that. Doesn't even matter what that is. I'm already doing it, I just want to keep doing it. I don't want to have to shift gears, change it to something else, come back to this. Like, you prefer to just what I'm doing, keep on doing it. Which leads us into this idea of something called inertia. It's the resistance to change in movement. That the science word for that is inertia. Okay. Okay, so we call Newton's first law of motion the law of inertia. Okay. We said inertia is the idea that objects resist changes in their motion. Whether it's moving, it's not moving, doesn't matter. It doesn't want to do something different. Okay. Inertia is caused because of the mass in an object. Okay. It's caused by inertia I'm sorry, inertia is caused by mass of an object. So if an object has mass, then it's going to have inertia. It's not going to want to change whatever it's already doing. Okay. All right. So that's where the idea, the more mass an object has, the more inertia an object has. And the phrase comes, an object at rest will stay at rest unless acted upon by an outside force. Sometimes it's called an unbalanced force. The opposite is also true. An object in motion will stay in motion unless acted upon by an outside or an unbalanced force. Questions on the first, any of the wording of what we've just said on the first law? Feeling good so far? Okay, good. Okay, so in the same idea, if an object is at rest, it's going to stay at rest until some force acts on it. If an object is in motion, it's going to stay in motion until some outside force acts upon it. Wait, but then why, for our soccer ball, does the ball stop rolling if it doesn't hit the net and it doesn't get kicked by another player and it doesn't interact with things? Why doesn't it just keep rolling? It is round, but you would think that's helpful. So it is being acted upon by outside forces. Some of the forces you guys have listed, but the idea is it is being acted upon by outside forces, which is what causes is its motion to change. So it's being acted upon by air resistance. It's being acted upon by friction with the ground. It's being acted upon by gravity. All of the things are outside forces that are acting upon my object. Okay. Making sense? Are we good with what we're talking about so far? Okay, good. Good. Want to make sure it's not overly confusing. Good. All right. So take a moment and think about my two questions that I'm going to ask, my two examples. Don't say anything until I ask you to. So, in the first one, which has more inertia, a bowling ball or a tennis ball? Don't say anything until I ask. Which has more inertia? You shouldn't be typing because I told you don't say anything yet. Which has more inertia, a bowling ball or a tennis ball? And be prepared to think about why. Okay, go ahead. Which one has more inertia, bowling ball or tennis ball? Okay, good. So remember, more mass, more inertia. So, okay, so what if I changed that one? Because Just seeing the difference in size between a bowling ball and a tennis ball made it very easy to see that. But what if I change it to a bowling ball and a basketball? Okay. So good. So the idea here is it's not the size of the object, it is the mass of the object. So even with basketballs and bowling balls that are essentially the same size, it's not disconnecting you, Colton. I can tell from yours, it's your Wi-Fi connection is not good. It's not the no, it's not the classroom. It's your Wi-Fi connection. So, okay, how about the second group? The hammer or the feather? Yep. So which one has more inertia? Which one has more resistance to changing its motion? That's what we're looking at. Good. Good. Same idea here. The hammer has more mass, so it's going to resist that movement more. Good. Yep. Won't matter because, again, our idea there is that it would be resistant to that change because of its mass. Correct. Good. Very good. Very good. Fantastic. Okay. Last thing we want to look at before we take our first break here, our first little pause in what we're doing. The second little pause will be when we transition to our lab. Okay. So think about inertia like this. A car is a heavy object because it has a lot of mass, not just because of its size, but because it has a lot of mass. Okay. So if you had a person trying to push the car when it's not moving at all, it's very difficult to overcome that initial inertia. It doesn't want to move. Doesn't matter how hard you're trying, it doesn't want to move. Okay. Make it come up here. Here it goes. Okay. But if you apply enough force, it will move. Okay. Even if this person may not be strong enough. But you're going to have to overcome that resistance, which is that inertia, before it will start to move. Does that make sense? Good. So when I look at this, so we haven't gotten to mass acceleration. All the things you guys are putting up there, that's not really what's going on here. Because at this point, you're applying force to overcome that inertia. It's not there where we're looking at how much it is. It's how do we get it to move? And that's just applying enough force to overcome its resistance, to overcome that inertia. Questions? Just looking for where we are here. Good. Okay. So if you were going to move a bigger car, what would have to be different? If you were going to have to, there we go. That's right. If I were going to move a bigger car, going to have more force. Correct. Good. Okay. So conversely, smaller car is going to require less force to overcome that moment of inertia. Good. Okay. So the more mass something has, the more force it's going to take me to get it to move, get it in motion. Now, what about when it's already moving and I want to make it stop moving? Okay. So if there's a heavy car coming at you, what kind of force are you going to need so that it will stop before it runs you over? Because that's a bad thing. We don't want that to happen. Yeah. Yeah. Just a thought. Right. You're definitely going to need a larger force to stop a large, heavy car coming at you. Okay. Ah, there's your fear. Got your moment of fear. Ah. All right. We're going to pause here and take our break. Collect your materials during break. And when we come back together afterwards, we'll go through Newton's laws. Then we'll actually do our lab. So enjoy your break. See you guys in a few minutes. All right, so here are some examples, pictures of inertia just for fun as you look at those, just for fun. So remember, if something is going to be resistant to changes in its motion, it doesn't want to move if it doesn't have to. So these are kind of fun examples. So if it's already in motion, it doesn't want to stop moving. If it's not in motion, it doesn't want to start moving. Okay. So in the first picture, top left, you'll have the picture where the motorcycle actually comes in contact with an object that causes the motion to stop. However, the rider does not come into contact with that. So, Houston, we have a problem. Yes. Yep. Second picture on the top right, you'll notice if you are on a train, you have a bottle, for example, that's sitting still. When the bottle starts, I'm sorry, when the train starts moving, the bottle doesn't want to start moving with it. It's going to resist that. So it will actually roll backwards. Then, once it's already moving, if the train were to stop, again, the bottle does not want to change its movement. So it will keep moving and roll forward. So those are some examples. And then the last one, that machine actually shakes the trees to try to remove ripened fruit. But remember, the fruit does not want to change and go into motion like the rest of them. So sometimes the force of gravity will overcome that and it'll literally just fall out of the tree. So some kind of fun and interesting examples of inertia. All right. So some examples of things that are forces that could cause motion to stop. Things like gravity, we talked about earlier with the soccer ball. That could cause motion to stop. Things like friction from the movement for opposing that motion could cause it to stop. Things like a barrier when you saw an object go crash, boom, bang, right? A barrier can cause an object's motion to stop. Okay. All of these are sample types of oppositions. Okay, so then when we talk about friction, what are we talking about? So if you haven't studied it before, friction simply means the resistance that an object encounters when it's moving or rubbing against another object. And friction always causes the motion of an object to slow down. It always decreases the motion because it acts in the opposite direction or it acts to oppose the motion. It's the way that it works. Yes. Okay. Good. So then when you look at the last one, at the picture at the bottom, it shows you okay, if there is a force pushing on the object, then the motion is going to go in the same direction as the force, and the friction is going to be pushing in the opposite direction. So it just gives you a visual for what that looks like. Okay. So, here we go with our lab all about friction. Now that you have at least a general idea of what we mean, we're going to look at this. So, I asked you to have a large book, doesn't matter what book that you have. Um, if you have a textbook, if you have a book that you read in your house, doesn't matter. Just not like a novel size book. We want like an actual larger textbook. Then you're going to need a paper clip, a small pencil-topped eraser. I'm looking to see if I had one on my desk I could show you. I don't. And then 2 lumps of clay and a ruler. So here's what you're going to do. You're gonna lay the book flat on a table or on your desk or even on the counter if you need to do that. You're gonna take one of your lumps of clay and just roll it into a ball, okay? And you're going to take another of your lumps of clay and just flatten it into a disc, like a little pancake, okay? As far as the size of your lump of clay, it just, kind of a one that fits nicely into the palm of your hand. It doesn't need to be a large piece of clay, okay? Once you have done that, you're going to line up all the objects along the short edge of the book. What do I mean by that? I'm trying to show you here. So if this is my book, right, it's lying flat on my table, I'm going to put all of my objects along the short edge of my book. Okay. Then I'm going to slowly lift the book up, raise the book until the first item slides. And when it slides, I'm going to freeze and get my ruler and measure the height. And you'll go, so if I'm measuring the height of my book, I would go from the table or counter or whatever to the top because that is the surface where the objects are sliding down. So I'll lift it until the first object starts to fall, then I'll stop and measure the height, then I'll keep lifting until the next item falls, stop, measure the height, keep lifting until the last one falls, stop and measure the height. Okay. So on the first run, the objects that you're using are going to be the paper clip, the eraser, and the ball of clay. So you're going to do that. You have a total of 3 items. So lift it till the first one goes, measure the height, record that. Lift it till the second one goes, measure the height, record that. You'll have to go slowly because if you go quick, it's going to dump it off and you won't really get an accurate measurement. Once you have completed that one, you're going to do the same experiment again, but this time only using the ball of clay and the disc of clay. Okay. Questions on what you're doing here? Anybody with questions? Maybe there's a couple of different versions of the book. Everybody's textbooks don't look the same. Some of your textbooks have soft sides. So when you start lifting it up, it starts like bending. You want it to be a hardcover book. If not, it'll make it more difficult for you to actually get your measurements. All right. Anything else you can think of here? So you're looking at your little sheets here that you're going to record your data. If you notice, there is a hypothesis section. Now that we have explained what you're supposed to do, you need to predict the height when the items will slide for each of the 4 items that you're going to use. Now that you understand what you're doing, go ahead and make that prediction. So do that part first before you actually get involved in any of the performing. Prediction first, yes. Okay. Once you have made your predictions, it already falls, so you don't have to put it. Yep, that one tends to go pretty fast. But yes, if it's already fallen, there's no need to put it back on there. It's already fallen off. Good. Just reading through your comments here. And so for this one, I ask you that raise it until the first item slides. That's when you're measuring. Doesn't have to fall off completely, just until it starts to slide. Of course. So you're doing this, you do a predicted height for each one. Then once you've done all your predictions, actually test them, measure your height, record that, and then it's got 2 questions that you need to answer. If you keep raising it, eventually it's going to get almost horizontal. I mean, I'm sorry, almost vertical. So at that point, at least should slide unless you pressed it onto the book. It's fine. Good. Just reading through everybody's comments. Those are all fine. Okay, nope. For the first one, you're supposed to use the paper clip, the eraser, and the ball of clay. Those 3 together and measure. Then for the second time, you do the ball of clay and the disc of clay only. Is that better? Okay, good. So do that, record your data. In about 2 minutes, we've got a little bit more to finish up talking about for the day. And then we're going to go to your activity that you're going to do today or for this week, not necessarily today, but for this week. Okay. All right. Once you have collected all of that data, record that so that then you can answer the 2 discussion questions at the bottom. Good. Just about another, I don't know, less than a minute. Definitely not a lot of time left. If you're finished, you can answer the questions at the bottom, but we're getting ready to move on to the next thing, just so we have time to finish answering and addressing all the things, and so that we also have time to talk about um, the challenge for this week. Okay, getting ready to move on. So finish up with where you are now so we can go through what we need to get you through here. Good. Okay, looks like most of us have at least gotten a good amount of the work done. So, yay for us. Yes. And thing to keep in mind here is just to make sure that you are able to follow along with what we're doing in the last part, because for this, it's really going to be focused in on kind of understanding the rest of Newton's laws. Because part of what you'll do in your lab this week is to investigate that. Okay. So here we go. When we're looking for this formula for force, okay, we're looking at force being a method of acceleration first, so changing the velocity over time, and the mass. That's why the formula for force is that force is equal to the mass of an object times its acceleration, because that's what it comes from. Taking some mass of an object, putting it in motion. So force is the mass of the object times its acceleration. Now, force uses a really weird unit. That unit is called a Newton. So a Newton has kilograms, meters, and seconds squared. Okay. So you would measure a force saying it's a 10 Newton force, or um, it's a -5 Newton force, whatever, if it happens to be, because you have to put a direction with it. Okay. Okay. So we talked a little bit earlier about what mass was. So force equals mass times acceleration is Newton's second law. Okay. Then the third law says for each action, there is an equal but opposite reaction. So it is a response to the initial action. Okay. So I've given some examples here where you can see both actions and reactions. Okay. So in the first one, you see a balloon that's been completely inflated. When you let go of the balloon, the air will quickly rush out of the balloon. That is the action. The reaction is that the balloon will then float away by that force that's pushing out for the air. The opposite reaction is going the other direction. Okay. The same is true for something like a rocket taking off. As the gas and liquid is being expelled from one end, it propels the rocket up. Okay. That's another example. Then the one that you see if when someone is paddling, right? If they're paddling in a canoe, so as they push on the canoe, on the oar to push the water back, that's the action. The reaction is that the boat is propelled forward. Okay. Same thing would happen if instead of pushing it with an oar, you were simply standing on it and you were to jump. Your action when you jumped would actually push the boat backwards. Okay. And then when you look at firing a gun, the force used to push the bullet out of the barrel, the reaction is that recoil that pushes against either your hand or your shoulder, wherever you are firing the gun or whatever your grip is when you're firing. So, just some examples of Newton's third law here. Each motion has that equal but opposite reaction. All right, here are a couple of questions. I just want you to take a moment to consider them by yourself before we talk about them together. There's two scenarios. Take a minute, read them both, think about them, then we'll go do something with them. Hold on, you're supposed to be thinking about it. Hold on. Okay, so give me some feedback. On the first one, it says, you dribble a basketball while walking on a basketball court. Give some, at least three, but I want you to just give one, pairs of action reaction forces that would happen in this situation. Okay, so those aren't really a pair. The hand pushes the ball and the ball bounces because there's no reaction to that. It's both the same action. But the sidewalk doesn't truly move backwards. Basically, you push against the floor and the floor pushes back up against you to propel you forward, right? So the it mirrors that. It doesn't actually move, but it does. Yeah, there it goes. Anybody else? Okay. So if you're thinking about the actual um, reaction action pairs, you pushing down on the ball, right? So when you push the ball down to the ground, there's a recoil of your hand coming back up. Or when you or the ball pushes against the ground and the ground pushes back up to cause the spring or the movement, things like that. All right, here's another example. It says, when Jane drives to work, she places her purse on the passenger. Oh, wait, pause. We're almost out of time. What am I doing? We got to pause on that one. I just realized. I need to go through quickly what you're going to do for your balloon car challenge. This is an example of the directions for how to do it, which I will post on our class page. Okay. You're going to make yourself a balloon car. It's kind of fun. It allows you to see Newton's laws. So let me post on here. There's a video in our class page. It's already there. The lab directions probably won't come up until class is officially over. But you are going to build a car like this. And then you're going to be responsible for how it shows Newton's laws. Okay? And so the video walks you through how to build the car in addition to the directions doing that. Okay. So, do you understand what you're going to do? You're going to use your materials. You're going to build a car that looks like this. What you're going to turn into me are going to be two things. One of the things is going to be a picture of the car you built. I want to see what you did. That's the cool part. Like to see the work you've done. And the second thing is an explanation for how your car shows Newton's three laws. Okay. The directions are on the video. They're also on the balloon car challenge assignment so that both are available for you. That's okay. I was just showing the video to show that you could find it there. It looks like this. There was nothing there on that was worrisome. This exact same video is posted on our class page along with the directions so that you can use that because you have to turn in a picture of your balloon car that you built as well as explaining how that car shows all three of Newton's laws. Okay. So for this week, your things. Thing one, you're going to do some reading. Thing two, you're going to finish the lab report that we were doing earlier for the friction stuff. Okay. Thing three, you're going to build your balloon car. Okay. Your Newton's Laws lab report, the friction lab that we were doing earlier, should be finished or almost finished already if you came to class prepared. Okay. And then the last thing you're going to do is you're going to do an e-lab where you don't have to worry about having materials. You just get to kind of set up and play with different parameters and see the labs work. This week, I tried to really focus on more hands on things. You don't have a lot of written things this week. It's more about actually applying the labs and getting to see it and do that. So, I hope you have a fantastic week. Enjoy your fun activities, and I look forward to seeing you again next week, everybody. Have a good week. See you next time.